Hello, let us look at our first question. Let C1 be the set of all differentiable functions, actually continuously differentiable functions, on this closed bounded interval 0, 1. In first part, we need to show this function is indeed a metric on C1. In the second part, we need to show that this inequality holds for any functions from this L infinity. Okay, let me also add for all f g in L infinity. Okay. By the way, this L infinity is not L infinity, of course. It's different. C1. C1 0 1. Okay. So let us recall the definition of a function being a metric. So here's my definition. So let us show first property. M1 is satisfied. So let me put M1. Okay. So as you can see, each part of the function, for example here, it is always positive. This is also positive. So this first property holds, right? The rho, I mean, fg is always positive or 0 for all fg in C1 0 1. Yeah. Now let us show it is 0 if and only if x equals to y. When x equals to y, when x equals to y, this is 0, right? For example, if I take the same function, okay, f. So let me write it f and f. Since we are just subtracting from the first, okay, the 0 point, it is 0, right? So this part, first part is 0. Okay, let me write the definition. I mean, minus f0 minus sup blah blah f prime t minus f prime t in 0 1. This is always 0, this is always 0, so it is 0. So let us show the other way around. If this is true, this is true. We have just shown. If this is true, let us show it should be the same function. Assume rho f g is 0, right? I mean f 0 minus g 0 plus supremum t minus g t t. Okay. Now if it is 0, then since this and this both positive, they should be 0 at the same time. So this should be 0, right? So f0 should be g0, and this f t minus g prime t should also be 0 for all t. If you recall something from the calculus course, if their derivatives are equal, and if they are equal at some point, it means that they are the same function by the fundamental theorem of calculus, etc. Okay, let me prove it very easily. This implies ft is equal to gt for all t. Now take the integral. Then I have ft equals to gt plus some constant. But I know this constant should be 0 because if you plug 0, put 0, then you have f0 equals g0 plus constant. Since they are equal, this and this are equal, c must be 0. So f and g are equal for every t, it means they are the same function. So we have just proven the first property. So let us show the M2. And let me separate the calculation. Okay, symmetry is very straightforward. Check that, obvious. Rho fg is equal to rho gf, because when you put, you can change the places. It is in the absolute value right here in the definition. Let me show you. Okay, probably you don't see it. Now you might see. If you change the roles of G and F, this is the same. Again, since it is also in the absolute value, it is the same, so they are equal. So let us show the M3. Whoops. Yep. M3. So I need to show the triangle inequality. Okay. First, given any f g h. Okay. So let me write rho f and g. This is the I'm just gonna write the definition. F 0 minus g0, but let me add h0 and put again, so I don't change anything, right? This is still 0. I get the same definition. So plus supremum f prime 0 minus g prime 0 minus h prime 0 plus h prime 0. Not zeros. Oh, sorry. They should be t, of course. T. T. Okay. T in 0, 1. Now observe the following. Observe for any t in 0, 1. This f minus t minus g minus t is less or equal to f minus t minus h t plus h t minus g t. This is by basic triangle inequality from the real analysis, right? Yeah, calculus, I mean. So this holds for ht. So since supremums are the least upper bounds, they should be preserved under this inequality, right? So the supremum of these things should be less than this, and their supremum also bigger than this. So sup. I know this is a bit tedious, but I want to give it the full proof, full detail. 1 less or equal supremum f prime t. Yeah, I'm just gonna write what I verbally explained already. Plus sup h prime t minus g prime t in 0, 1. Okay. So let me make a space. Okay. Now, using this observation, at the end, I can show that this rho fg is less or equal to f0 minus h0 plus. I'm just gonna copy and paste because it is a bit too much. F and h. So let me just copy this. Sup plus g0 minus h0. These two things are coming from here, right? So but they are less than. plus I also need to copy and paste the last thing. Okay. Oops. Okay. But they are equal to rho FH plus rho HG. Proves the M3. So we have just proven that this is indeed a metric. Okay. So let us recall the second property. We need to show that this inequality holds. And hint is MVT, mean value theorem. Okay. Second part. Let the ne oldu buna böyle? Be the uniform convergence metric. I mean DFG is defined to be supremum of F minus G for all T on this C1 is metric. Okay. So I'm gonna show that this D FG is less or equal to rho FG. Now we can apply the mean value theorem as follows. Oops. Şunu küçültelim biraz daha. Okay. Consider the function. First, okay. Şöyle devam edelim. Let's given f and g from the C1 0 1. Okay. Consider the function gamma x, or since we are denoting variable as t, let me put t, ft minus gt. Okay. So let us apply the mean value theorem to this gamma on the interval 0 t. Okay. Given o zaman o yüzden x diyecektim. Okay. Let me just rewrite it in terms of the variable x. Consider the function or define gamma x f of x minus g of x given t in the interval 0 1 closed. Apply mean value theorem since f g so me gamma are in C1, so they are differentiable, so we have the notion of differentiability. So gt minus g0 divided by t minus 0 is equal to some g prime c for some c in the interval 0 and t. This is the terminology of mean value theorem, statement of the mean value theorem from calculus. Now let us expand this gamma. So we have ft minus g of t. By the way, this t is arbitrary. That's why if I end up with some plausible or proper solution, it holds for each t in this interval. So we have just proven the theorem. We will end up with proving. Anyways, minus f0 minus g0 divided by t. Okay, is equal to some gamma C or F prime C minus G prime C. Now this T is positive and bigger than 0. It is not 0. Yeah, of course it cannot be 0 because we are dividing it by it. So T is positive. So we can just make this cross multiplication. İşler dışlar. So we have f of t minus g of t is equal to f0 minus g0. I just put this in the right hand side plus t in the parenthesis of f prime c minus g prime c. Okay. If you take the absolute value of both sides and you get, it seems a bit tedious, but I'm gonna give you the whole explanation. So this is gonna be in the absolute value. So you can apply triangular inequality in the real sense. So we have f0 minus g0. As you can see, we are getting to the point that this right hand side would be equal to the new metric rho. Okay, I'm getting to my point. This huge observation. Plus t f prime c minus g prime c. Okay, this t is less than 1. Yeah, even we don't need that, but it is less than 1. Okay, bigger than 0. Okay, less than 1. So this thing is also less than f of 0 minus g of 0 plus supremum f t minus g t. T is in 0 1. Okay, this thing is because t is less than 1, less than or equal, and supreme is always bigger than the any point that you are taking supreme of. Okay, so it is true, but at the end this last equation, the last term, is just the definition of rho f g. So we are finished. So let's look at this problem. Determine whether the following subsets are open, closed, neither. For example, let's look at set A. So A. Let us try to understand A. So as you can see, this is a graph of the function. A is a graph of the function f is equal to x cube y cube on R2. So it's like a surface. Okay, it's like a surface, so it has no thickness. It means that it cannot be open, and it will not be closed because we are taking this set. This is an open set, so image will be open. I'm expecting and I am observing. Okay, so I'm just gonna prove it. Claim A is not open in R3. Of course, we are dealing with the classical topology on R3 or classical metric on Euclidean metric on R3. Classical topology or metric. I mean Euclidean. You will see that the metrics are equivalent on this Euclidean space Rn. You will see that. But yeah, maybe you have already seen it. Anyway, so A is not open in R3. So let us prove it. Consider 0, 0, 0 in A. So it is, as you can see, it is in the set, right? if you put 0, 0, 0, because 0 square plus 0 square is less than 1, so 0, 0 can be evaluated. 0, 0, 0 is in the set, of course. So given any, assume it is open, assume A is open, so there should be an open ball, be centered at 0, 0, 0, with radius epsilon, should be in A, right? By definition of openness. But it is wrong because I can explicitly show that, but this is wrong since consider 0, 0, epsilon over 2 for example. Şunu daha güzel yazayım. Epsilon over 2 in the ball 0, 0, 0 epsilon, but this is not in the set, right? This is not in the set A, but 0, 0 epsilon over 2 is not in the set A, because if it is in the set, it should be a non-zero, right? But as you can see, it is 0. When you put first and second coordinate as 0, 0, the third one should be 0, but contradiction. So it is not in the set, so A is not open. I can not similarly, but show that A is also not closed. Claim A is not closed. Before that, in R3, before that, let me show you or explain my motivation. So in R3, it is like a surface, okay? It is like a surface, something like that, some surface, okay? So as you can see, at each point on the surface, if there is a ball, they exaggerate these points outside of the surface. So there are points for each ball outside of the surface, so it cannot be open. It is the explanation for the first claim. For the second claim, since the boundary is not open, so the boundary of my is open disk, okay? So if we have a surface, something like that, but I am intersecting with this open cylinder. This cylinder. So when you intersect these two surfaces, you get some piece of a surface, but which is not closed because it does not include these boundaries, okay? That's why it will not be also closed. Non-closedness, non-openness. Okay, let me show it is not closed. So one of the ways showing some set is not closed is to consider the limit points. Consider the sequence n over n plus 1, 0 in R2. Now let's look at the image or the implementation of this in this set. Okay. Or let me just directly take this sequence. Whoops. Or no, okay. Let me explain fully. This be my sequence in R2. It is in R2. Consider we have f, x, y defined to be y3, f takes points from this set x squared plus y squared less than 1, and it is real valued, so it goes to R. So obviously f is continuous, a polynomial. That's the explanation. So let me make me a space. Okay, since f is continuous, we can take the limit. Okay, consider limit and goes to infinity. By the way, this is not just a subset of R2, but this is in the set. Okay, yeah, I cannot say that. But the first two are... okay, I can say the following. Okay, this is subset of x squared plus y squared being less than 1. Because square, this is less than 1, this is 0, so this is always, every point of this is in this set. That's why it is true. Now I can finish my claim. Take the limit of f n over n plus 1 and 0. Since f is continuous, I can evaluate the limit inside. Lim n goes to infinity. N over n plus 1 and 0. So this is just equal to f of 1 comma 0. This should be in the graph, but it is not on this graph. This graph, I mean the set A. So it shows that it is not closed because it does not consist of all limit points. More explicitly, each of these image points are in the A, right? The set of A. So each of these points are from the A. But when you take the limit, this limit point, this f of 1 comma 0 is not in the set. It means that it cannot be closed. So A is not closed. Now let us look at this following set B. Is it closed or open? I claim that it is neither open nor closed, but first let us observe something. Okay, let me make you a graph. Okay, this is x, this is y. Of course, there should be some difference in the coordinates, but okay, let me just focus on my following example. Consider the graph y equals to sine x. So it's like starts from 0, goes to -1, 0, blah blah blah, yeah, to the infinity. So now let's look at this set as x in the real axis such that sine x is bigger than 1 over 2. How can I analyze this set? So to be able to write this set, you need to have some line. Okay, let me make you a line. Okay. Kötü oldu. Let me create the example from the stretch. Okay, because I want you to see the exact lines. So this from here, etc. So let me make another line. This blue thing is y equals to 1 over 2. And let me also write this axis, xy. This set S is only consisting of the points whose sine x is bigger than 1 over 2. So I'm just gonna take the values of x. If you evaluate in the sine, they will be bigger than 1 over 2. So I am looking at the points of these things, right? These things. I don't care about the other points. I only care about the bigger things, bigger sin x than 1 over 2. So when you take them, okay, when you take them, it is these following intervals. For example, here also you will have some interval like this after some, blah blah. So at the end, your points will look like the following infinitely intervals. Okay, blah blah blah, until infinity. So, but we are living in the R2, but they are not closed and open, because they are not closed because they don't consist of these limit points, okay, at the boundary of each piece. And they are not open because if you take a point here, and if you take a ball, arbitrary ball, they will consist of other points other than these intervals. For example, there exists a point, let me put it purple. This purple point, let me call K. K is not in the set B, but K is in the ball. So it contradicts the openness. So it is neither open nor closed. Is neither open nor closed. So I can also give you the further calculations. So the following would be the exact graphing of the set B. So let me also give X and Y. So the following things is true graph. So this is graphing. So yeah, this B is equal to this yellow points, no, green points. So these greens, they go to infinity, but they lie on the axis Y. As you can see, your X values or X coordinates are always 0, but your Y values are corresponding to these points in the following set S. So it's like the following graph. As I already explained, it is neither open nor closed. And to be able to show this exercise similar to A, you can follow the ideas from the part A or the set A that I have just calculated above. Okay, you can do the same reasoning and you can show it is neither closed nor open. Okay, so let us also analyze the set C. First, let me recall the set C. 1 second. Nerede bu? Cosine T, sin T, and T is from 0, 10. So first let me draw it. Then I get a feeling, then I can prove what I need to prove. This is 2, not 1, of course. Let me make a space. Let me draw it. This would be my axis. This is x-axis, this is y-axis, this is x-axis, this is y-axis. So if you draw it, since I only need 2 pi, okay, to be able to write this thing, because this thing is circle, right? This is a parameterization of circle. C is the parameterization of the circle with radii 1. So it gives me the circle. Let me try to make some circle. Haydi bakalım. O yaptı. Güzel. It's not what I expected, but okay, fine. Tövbe tövbe. İşte olsun istiyorum ya. Probably. So this boundary çok dandik ya. İstediğim gibi olmuyormuş. Border istiyorum. Probably. Okay. So this purple thing is my set C. So this is my set C. This is the whole circle because you wrap your circle more than once. Because even 2 pi is enough, right? And it is approximately 7 point something, but it is obviously less than 10. So obviously you wrap your circle more than once, but since it is a set, we don't regard copied elements in the set, so it is the same set. Okay, this is a circle S1, and as you can see, this S1, this circle is closed. Okay, because it consists of all the limit points, but it is not open because, for example, take this point P, take a neighborhood, take a disk, closed disk, open disk. As you can see, there exists always a point outside of this ball. So C is not open. Again, the idea of showing this is not open, similar to the ideas that we have dealt in part A, but let me sketch it for you. Consider the North Pole. Consider the North Pole 0, 1 in the circle. Okay. Given any ball B at 0, 1 with epsilon. Okay. Now consider 0, 1 plus epsilon over 2. As you can see, this point will lie on this point, this ball. Okay, so I'm considering the new ball for convenience. So I'm considering the following ball. This is my radius epsilon, and this would be my point. This is my point 1, 0 comma 1 plus epsilon over 2. As you can see, this cannot be in the circle because when you take the square it will be bigger than 1, but my radius is always 1, so it cannot lie on this C. It cannot lie on this set C, but this 0, 1 plus epsilon over 2 is on the ball 0, 1 epsilon. It's contradiction, so it's not open. Okay, so it's not open. So it is closed. We can show it how. Okay, first C is equal to the following set: x, y, x square plus y square is equal to 1. If you can show this is true, okay, show it. It's true. Then part II, you can also write this following set as follows: f x y is equal to x square plus y square minus 1 is being 0. So it is just inverse image of the close point 0, where the f is, of course, I already defined here. So you can show that f is continuous function, right? It is just a polynomial, so it is continuous. So any point is closed. So inverse of a closed point is closed. So this is closed. Is closed as the pre-image of a continuous functions at a closed set. So by definition of the continuity, it is closed. Let's look at the third question. So let us continue. Let us consider this L infinity. Recall it. This L infinity is the space of all bounded sequence. So they are just real sequence, right? Indexed by indexed by the set of natural numbers, and they take the values in R. Okay, so it's like a function space, R to the power n. Yeah, it is true. So we need to understand this set A is open or not. Of course, yeah, is open or not. My claim is it is open by the following observation. Informal observation. Okay. I'm gonna show you how I think in this kind of sequential problems. I start by writing the natural numbers 1, 2, 3, 4, 5, etc. So they are just my index set n. So as you can see, at each natural number, okay, I have a point. Okay, they are just xn. For example, this is my x1, so this is my x2, so this is my x3. Since this is bounded sequence, it cannot reach. Yeah, each point is defined, so they are just real numbers. I can just put them, okay, for finitely many numbers. For example, x5, etc., etc. So I will have a bunch of points, okay. So in this question, it says that every point in the set A has the second value is bigger than 2. Okay, this second index should be bigger than 2. So it means that if you make a line, horizontal line, okay, olmadı bu. Okay, something like that. This is the line 2. So your second index should be above of this line. Okay, this is the informal observation. So prove it. Yes, A is open. How do we show some set is open? You need to take arbitrary point from a set, then you need to find a ball that is entirely in this set. So let me start by taking an arbitrary point. Given let A and B any point in A. Yeah, by point I mean a sequence, of course, because in this kind of setup, your points are corresponding to some sequences. That's why I'm taking point or sequence. Yeah, they are just same thing. Now consider, okay. So in this setup, at my index 2, my A2 is bigger than 2, right? This is my 2 line, and my A2 is bigger than 2. I am following my informal observation, right? Since AN is from the A, my second index of A should be bigger than 2. So A2 is strictly bigger than 2. Now consider the ball B, let me define by B, the ball at point AN, the sequence, with radius A2 minus 2 over 2. Okay, so my idea is the following. A2 minus 2 is this length, right? This length is equal to A2 minus 2. If you take the half of it, you get this radius, right? So you get this. So this thing is A2 minus 2 over 2. Right? This little half of the radius. If you do this, and if you take any point from this ball, they would be automatically in A, because their second index cannot exceed this A2 more than A2 minus 2 over 2. That's why their second index, or I mean for any xn from this ball, the x2 should be also bigger than 2. It means that it is in the set A. It means that this ball is entirely in the A. Okay. My claim, my finishing claim is that ball is entirely in A. Okay. Hence shows that A is open. Because I have just taken any arbitrary point, any arbitrary sequence in the set, and if I can find the ball entirely encloses this point and entirely in this set A, it is finished, right? So I need to show this. So given any xn from the ball means supremum xn minus a n in the natural numbers should be less than a2 minus 2 over 2. Okay, so it means that let me consider the a2. So this supremum is bigger than x2 minus a2, and this supremum is less than a2 minus 2 over 2. So let me rewrite it. So is less or equal to a2 minus 2 over 2. So if you expand this, okay, if you expand this inequality, you will have 2 minus a2 over 2 is less or equal x2 minus a2 less than or equal a2 minus 2 over 2. Okay. So if you add each thing to a2 over 2, okay, plus a2 over 2 to each side. So let me make some space. So you will end up, we then have 1, okay, less or equal x2 minus a2 over 2 less than or equal a2 minus 1, right? But let us focus on the first inequality. So we have 1 plus a2 over 2 less or equal to x2, and we know a2 is bigger than 2, so a2 is strictly bigger than 1, or 8 over 2 I mean. So this thing is strictly bigger than 2, so x2 is bigger than 2, so xn is in A as claimed. So it means that it is open and we are finished. So let us try to understand such a question. It is a bit weird because in metric spaces, of course, in topology, there is something called indiscrete topology, which is just consisting of the empty set in the topology and the whole set. But if you try to mimic the topology to metric space, you will end up with indiscrete metric. But to be able to talk about some indiscrete metric which makes some sense, your space y should be just 1 point. Okay, so there is only 1 point. Okay, so in discrete metric, rho is defined by the following data for any x, y from matrix on y row x, y is always 0. Okay, so if you recall the first piece of the definition of being a metric, this should implies if and of course this is if and only if x equals to y. So if you define your metrics as trivial as this, you only have to have just one point. So by the definition, M1 in being a metric, y must be a singleton. So this is my first observation. Now it comes to the following problem. Let us given a function from x to a singleton or point, maybe let me write it in this following way, point or y, then I need to show this is continuous function. Okay, this is continuous. But I can show the following: given any open set v subset of y, but we don't have any open set. We only have this point. Okay, so v is either empty set or a point pt. So f inverse image of empty set is by definition of empty, right? So check f inverse of whole set v y I mean, yeah, or point. So it means this function is taking the every point. So this is x, so it is also open, so it is also checked. So f is indeed continuous. Yeah, I know that this is a bit trivial, but yeah. So continuous as every pre-image of any open set open. Okay. Exercise: f between y and x and y, where x is discrete metric space, then f is continuous. Okay. This discrete metric space, you know that if they are zero, if and only if they are the same point, the metric is always 1 if they are the different points. Okay. This is a very good exercise. You should definitely solve this. Okay.